along. I'm just going to keep going for it here. Let's build up the helium atom. Can we do it? As it turns out, we can't, but I'll talk about why. Okay. So we start by putting the fact together that we have 2 electrons that we're now dealing with. Okay. And the 1 and the 2 right here corresponds to each of those electrons. So we would have electron number 1 that's got some radial dependence, and we've got electron number 2 that also has some radial dependence. And so through our separation of variables, right, we make a product out of those, okay, which means that our Hamiltonian is going to be a sum, okay? It's going to be, right, the operator for electron number 1 plus the operator for electron number 2. And when we apply that total Hamiltonian through this wave function, right, psi of electron 1 and electron 2, this will then commute algebraically, and our energy solution also becomes a sum. All right? And so then, of course, we could plug all that back in and still satisfy our simple Schrodinger equation. So what would that operator look like? Well, we would have for electron number 1, right, we would have a kinetic term. So I'll abbreviate that by saying EK for electron 1. And then, of course, we've got a potential energy term for electron number 2, or excuse me, for electron number 1. Then we also have a kinetic energy term for electron number 2, as well as a potential energy term for electron number 2. Okay, so let's put all of those subtraction signs. So, right, we're seeing kinetic energy and potential energy for electron number 1, kinetic energy and potential energy for electron number 2. But now, what about this other term right here? Well, as it turns out, if we kind of compare this term to our Coulomb's law, right, E squared over 4 pi R12, okay? This describes the electron-electron interaction. And so that's described as a potential energy. Okay? So there's potential energy between the 2 electrons. And you also notice that it has an opposite sign. So I'm going to say plus V12. And the reason why it now has an opposite sign is because, recall, a negative potential describes an attractive interaction, right? So V is less than 0, it's attractive, which makes good sense when we're talking about an electron-proton system. When V is greater than 0, it's repulsive. And that makes sense when we're talking about an electron interaction, right? They're going to repel each other. They're going to want to separate from each other. So that's why it's a potential energy term, because the electrons are forcing each other to separate. Well, as it turns out, just by adding this little extra term right here and then attempting to solve this Schrodinger equation through our normal means, it fails. There's no analytical solution available. And what we mean by analytical solution, there's literally no solution to our differential equation that evolves from putting this whole Schrodinger equation together, okay? Right? Imagine like smashing this whole operator into our Schrodinger equation and then applying the separation of variables. You know, each one of these psi of R1, right, it equals R of R1 times Y of theta 1 phi 1. But if we were to put that whole thing together for both electrons, we would have 2 of these R terms, 2 of these Y terms. We'd throw that operator in there and it would fail. We would not be able to solve this thing. And the biggest reason is because these electrons interact, okay? As it turns out, if we didn't have to have this last term in here, this system would be solvable. However, it wouldn't be very accurate because we know that electrons interact. Okay? So lots of approximations are required. And we're not going to spend a whole lot of time in this class going through those approximations because that's where the entire field of molecular modeling is born. Okay? And when we get into chapter 10, when we start talking about more with molecules, I'll mention a few of these methodologies. If you took molecular modeling, Chem 330 with Josh Smith, you talked about density functional theory. That's one way of approximating these multi-electron atoms and molecules. Hartree-Fock is another method. So there's all kinds of named methods that go into making these approximations. And all of them rely on using a computer to solve the problems for us. Okay? So I'm just going to talk about those things briefly in chapter 10. For now, I'm just going to kind of move on. And we're not going to worry about solving the helium system. But what we are going to talk about is the consequences, some other consequences of having 2 electrons in a given bound state. Okay? So one of the big ones, the Pauli exclusion principle. And this is all something you've heard before from general chemistry. Perhaps you just don't remember, and that's okay. So, as a reminder, Pauli exclusion principle says no more than 2 electrons may occupy a given orbital. And if 2 do occupy the same orbital, their spins must be paired. And by paired, right, we mean up-down, right? The spins must be paired, okay? And a special case of the Pauli exclusion principle that's less discussed in general chemistry because it involves complicated wave functions is the following. When the labels of any 2 identical fermions, and an electron actually is a fermion in particle physics, when the labels of any 2 identical electrons are exchanged, the total wave function must change sign. So what do we mean by that? Well, if we go back to our our helium wave function we were attempting to put together, psi 1, 2, where the 1 is the label of electron number 1, and the 2 is the label of electron number 2. Okay? Well, suppose I just exchange those labels. Let's just say I don't know which is which. Heisenberg tells me that's the case anyways. Okay? Well, when I do that, according to the math in the Pauli exclusion principle, which we're not going to get into this math because, again, that involves a lot of approximations. But the big one to note is it must change sign. It must go to negative psi 2, 1. Okay? This is going to be really important for establishing our multi-electron atoms from a conceptual point of view. So this is really important conceptually. Okay? If we change the position of those electrons, we literally just say, well, what if I just switch 1 and 2, switch their position? The wave function must change signs, according to Pauli exclusion principle. All right? So let's keep going with this. So when we look at this situation, psi 1, 2 equals negative psi 2, 1, we actually will get 4 possible spin states. Okay? And so just so we're clear on here, my nomenclature, alpha corresponds to a spin up electron. Beta corresponds to a spin down electron. The number 1 is electron number 1. And the number 2 is, you guessed it, electron number 2. Okay? So how do my 4 possibilities work out? Well, I have one possibility of just alpha 1, alpha 2. So in other words, where both of them are spinned up. That's one possibility. Okay? I could have both of them in the beta spin state. Both spin down. All right? That's a second possibility. I could have them paired up, like we talked about. Alpha, beta, right? Spin correlated. That's a third possibility. And I could keep them paired up, but then switch the positions. Okay? That is my 4th possibility. Okay? But because Heisenberg says we can't know which is alpha and which is beta with any certainty, we need a superposition of spin states. Okay? And so here is how that superposition goes. We'll create a sigma plus 1, 2 spin state, and that's already been normalized. So this is the normalization constant, okay? And then here are the two, this is the basis set, right? And I add them together and it creates the superposition. And now the superposition we're going to create is by saying alpha 1, beta 2, or beta 1, alpha 2. So we just basically switched the labels, right? Electron number 1 was alpha and electron number 2 was beta. Now we switched that. Another superposition is possible by changing the signs. And so that's sigma minus 1, 2. And again, we get that by literally just changing the labels, okay? So we have the sigma plus 1, 2 state and the sigma minus 1, 2 state. And it's important to note these sigmas, these are the spin wave functions. So they are wave functions that we're not going to go into. I'm not going to come up with equations for all of those and so on. They're just an additional portion of a wave function we would add to a multi-electron atom that describes those spin states. And it actually has to do with the fact that the electrons are interacting. Part of that spin wave function is that electron interaction, because a spinning electron, right, a spinning charged object creates a magnetic field. And when we have another electron spinning in that vicinity, those magnetic fields can influence each other to actually be attracted to each other, okay? So we have this spin wave function. We're not going to worry about what that spin wave function says, what it is, but we can create a superposition of spin wave functions by considering the fact that we don't know with any certainty which one is up and which one is down, right? When I switch the labels of those, I don't know which is which, okay? So let's continue along. So now, if we put all of this together, my four possibilities become as following, okay? So I'm going to get a possibility that goes as, let's see where we're, yes. Okay, great. So I get a possibility that's going to go psi 1, psi 2, and I'll just remind you that psi 1, 2, we can do separation of variables and call that psi 1, psi 2, right? And then, of course, if both of those are spin up, we would tack on that additional spin wave function, okay? Another possibility is psi 1, psi 2, and beta 1, beta 2. That other possibility is now psi 1, psi 2, and the sigma plus 1, 2. So the superposition, and you know, so, excuse me, I said that with this state number 3, so it's really both state number 3, this third and fourth possibility that are suspect to Heisenberg by switching them, right? If they're both spin correlated and we switch the states, we don't know what's going on there, okay? And with these two states, it doesn't matter because when they're both in the same orientation, they both have the same effect of repelling each other, right? If they're not spin correlated, they're gonna repel each other, okay? So that's why we're considering a superposition with the spin paired states because they're paired, okay? So then, so one of those becomes psi 1, psi 2, sigma plus 1, 2. And of course, the other one is psi 1, psi 2, sigma minus 1, 2. And as it turns out, we can categorize these. We can group these together. and I'm going to group them together as following. I'm going to group these three together, and we'll keep them as a triplet. And I'm going to group this one together, and I'm going to call it a singlet. Okay? And so why did we group them together in this way? Well, once again, Pauli tells us that if we switch the labels of the electrons, if we switch their positions, the wave function has to change sign. Okay? Well, when we look at this sigma minus 2-1 state, right? So we know it was written as sigma minus 1-2. So what happens when we switch those positions? Okay? Well, when we switch those positions, I get the following: 1 over root 2 of, and so now follow me here, right? So this is going to become now alpha 2, beta 1, and this one's going to become minus beta 2, alpha 1. So let's put all that together. So that's going to be alpha 2, beta 1, and then minus beta 2, alpha 1. Okay? And if I do a little bit of algebra on this thing, I'm going to factor out the negative sign, factor out the negative 1 over root 2. And then when I do that, I get that this term will become positive and this term will become negative. So this is my positive term. And now I'm going to write that as alpha 1 beta 2. So it was written as beta 2 alpha 1, but because this operation is just multiplication, I can write it in the other order. And now this term, because I factor out the negative, is going to be negative. So that's going to be written as, let's see, I'll write that as negative beta 1 alpha 2. And now let's compare this really quick. Okay, alpha 1 beta 2 minus beta 1 alpha 2. Alpha 1 beta 2 minus beta 1 alpha 2. Okay, so let's see. What happened here? Did I make a mistake in my math? Oh, no, I did not make a mistake in my math because I have a negative sign right here. And so as it turns out, all of this will just equal negative sigma plus 1, 2. So that means, let me rewrite that up here, sigma minus 2, 1 equals negative sigma plus 1, 2. And because that switches signs, that one is the only acceptable wave function to describe my paired up spin state. So what does all of that mean? Well, what that means is when we have two electrons, okay, two electron system, we get two, count them, two possibilities for spin states. Those possibilities are a singlet, which I've highlighted in blue, and that singlet, the sigma 1, sigma 2, sigma minus 1, 2, that's the only acceptable wave function to describe the spin pair, okay? But what does that triplet correspond to? Well, that triplet could be both spin up or both spin down or some superposition, which I'll go dot, 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 dot. I'm going to put like, well, I can't really draw this very well. Or I'll just write this as the following. So well, we know that that's not acceptable. So really what it means is we've just switched the labels. Okay? So like if I put 1, 2, 1, 2, or what we have is 2-1, or 2-1. Okay? So, 2-electron system. 2 possibilities. A singlet state, which is a pair, or a triplet state, which is not paired. So that's the biggest conceptual detail I want you to take home from this, is recognize that a triplet state, even though it seems kind of confusing calling it a triplet state, it's triplet because it has to do with superpositions and uncertainty. Or the singlet state, which describes an electron pair. Okay, so moving on. So we recognize that what this means now, of course, for helium, there's only going to be one acceptable wave function in this fashion, because we remember that helium is 1s2. And because Pauli tells us no more than 2 electrons may occupy the same orbital, and if they do, their spins must be paired. So helium is a closed shell atom that must be described by a singlet spin state, which means its wave function has to be sigma 1, sigma 2, sigma minus 1, 2. And where does all of that come from? Well, it comes from what we call here this determinant, this matrix, okay? This matrix of possibilities where we have psi 1 alpha 1, psi 2 alpha 2, psi 1 beta 1, or psi 2 beta 2. And so if you recall in solving this thing, and the 1 over root 2 is our normalization constant, right, we do the diagonal, okay? So that's going to go as psi 1 alpha 1, right, times psi 2 beta 2, and then minus the other diagonal, which is going to be psi 2 alpha 2 times psi 1 beta 1. And if we were to do algebra on this thing and factor it out, right? Let's do that. We can factor out the 1 over root 2. We can factor out the psi 1, psi 2. And what we'll be left with is alpha 1 beta 2 minus alpha 2 times beta 1. And this is equal to our sigma minus 1, 2 wave function, okay? So for helium, only one acceptable total wave function because of the spin states, all right? If we were to do this for a helium excited state, which I'm going to show you next, so perhaps, right, 1s1, 2s1, and we were to go and do this matrix of possibilities, we would get 3 possibilities to describe this. And I'm not going to go through all of that. So what about any closed shell atom? Well, this gets intense because now, right, this could be applied to neon, argon, krypton, sodium plus, oxygen 2 minus, right? Any closed shell. And so by closed shell, right, we recognize that that shell, for example, the K shell or the L shell or the M shell, right, the entire shell, if it's closed, if it's occupied by all electrons, it's going to have to be described by a spin correlated state. And this matrix gives us our only singlet possibility to describe that wave function. And it gets intense. So this is called the Slater determinant. Okay? And so this is what's largely used in computation, right? In big molecular modeling or even atomic modeling. And you create this matrix by working your way through all of the number of electrons. So N is your number of electrons. So you'd work your way all the way over for that number of electrons, okay? And then the A's, B's, and Z's, let's see if I recall. Yes, so that's given just to help you keep organized for a given electron. So also the letters will give you the number of electrons so that you have a square matrix. Okay? So this gets really intense, but that's why typically people use computers. You have to use a computer to do this. Okay, moving along. So now what happens to our orbital energy level diagrams? Okay, well, we start with this simple energy level diagram just describing level n. Okay, when we put in our subshells, right, S, P, D, and F, hopefully you remember for hydrogen and hydrogen only, each shell, right, end state, is degenerate. Okay, and I'm not going to spend a whole lot of time with this because this is a largely review from your Chem 109. But when we start putting in multi-electron atoms, okay, we get an effective nuclear charge, okay, which is due to shielding of core and valence electrons, right? So for example, our core electrons way down here are going to shield the valence electrons way up here from the nuclear charge. So that means for multi-electron atoms, okay, the effective charge won't necessarily be the number of protons. All right? And a result of that is it splits the subshells. So subshells are split due to the shielding. And what ends up happening, the larger, the higher out you are in your subshell, the more shielded you are, so the less attraction you experience to the nucleus, which has a result of shifting their potential energies up. So for example, the 2p energy level gets shifted up slightly from the 2s level because it's not experiencing that full charge of the nucleus as much as it was if there's only one electron. Okay? And so that splitting goes, hopefully you remember this, right, from the good old Gen Chem days and inorganic, right? S orbitals are less than energy than P, are less than D, are less than F. Okay? So we see, right, 1s, 2s, and then we go to 2p, and then 3s, and then 3p, 3d, and then 4s, 4p, 4d, and then 5s, and so on. And also, if you recall, when we get into the really complicated atoms, you know, levels like 3d and 4s, right, they can shift around depending on how many electrons you have in there. And I don't want to spend a lot of time getting into those details because I think that you've talked about that ample in your inorganic chemistry class, and that's talked about quite a bit in general chemistry. Okay, I just wanted to give a little review, right? Remembering what happens to these orbital energy level diagrams for multi-electron atoms. Okay, and also remind you, we have to remember how to do electron configuration because what's coming next are spectroscopic term symbols. And it's good to have a working knowledge of electron configuration to do your term symbols. So let's just review the simple atoms, okay? Lithium, beryllium, boron, etc. All right? So we remember that lithium is a 1s2 based on its position on the periodic table, okay? 1s2, 2s1. It probably would help if I put a periodic table right here. And so we can write that electron configuration, right, as 1s2, 2s1. And because we know that helium electron configuration is 1s2, you know, we can use the condensed shorthand, right, by replacing 1s2 with helium, and that becomes helium 2s1. Okay? So, and then, of course, as we add more electrons, we keep populating those subshells. So I'll remind you, this is the Aufbau principle. When we have open spaces, our electrons will occupy those open spaces. So for example, when we go from boron to carbon, you know, from 2p1 to 2p2, that last electron for carbon is not going to pair up. It's going to go into the open orbital to make the lowest energy configuration, right? So these are all ground states, okay? And when we go to nitrogen, we still have an open p sub shell, so that electron will spread out into that open p sub shell. Only then when we get to oxygen, where we no longer have any open subshells available, will electron pairing begin. And I always like to remind people, even you seniors, right? Oxygen is a di-radical. 2 unpaired electrons. That's why oxygen is extremely reactive. Okay. Fluorine only has 1 open electron, and then of course neon is a full closed shell. Okay, so don't forget about how to do your electron configuration. Okay, so just to remind you, Hunds rule says an electron in its ground state adopts an electron configuration with the greatest number of unpaired electrons. Oh my God, what did I say? I said Aufbau. Hunds rule. Let's erase that. The Aufbau principle is the building up, right? Putting electrons into each successive orbital. So Hunds rule says greatest number of unpaired electrons, okay? So we recognize a singlet state is made by a true pair, but a triplet state is made by 2 electrons that are unpaired. So if we go back and look at these electron configurations for a minute, check it out. So this carbon state right there, that's a triplet state. Okay. I'm not going to get into quite what this 3 unpaired electron is yet. We'll get there soon. But this carbon, 2 unpaired electrons, that makes a triplet. Okay. So, for example, if we were to look at the helium atomic absorption spectra, okay, the helium AA spectra, we know when helium goes through its principal transition, from the ground up, right? It goes from 1s2 to 1s1 plus 2s1. Okay? So what is this 1s1, 2s1 state? Well, because that's occupying both a 1s orbital and a 2s orbital, it could be spin parallel, like a triplet. That would be a triplet state. Or, and because these are in different orbitals, they could in fact still be paired. Not necessarily, or spin correlated, right? Not necessarily in the same orbital, but all the same, that is a possibility. Okay? And what's pretty cool, when we observe this helium AA spectra, you have to have a really high resolution to do it, but you get a doublet. So, to us, if we're to zoom way out on that peak, like, so I'll this picture means like I'm zooming way out, then I might just have a really sharp looking peak, right? Like one single transition corresponding to this 1s2 going to 1s1, 2s1. But if I were to zoom way in on that, I would actually see that there is a doublet. And that doublet is due to the fact that we could have this 1s1, 2s1. It could be a triplet, or it could be a singlet. So we could get transitions to either of those cases, okay? And we have to now come up with an organized way how we can notate which one it is. Is the 1s1, 2s1 excited state a triplet state, or is it a singlet state? How do we know, and how do we notate that? That's where we're going to go next, okay? And just to give you a preview, that's where we're going to have to get into this total spin quantum number J. Okay, so that is coming next, folks. I will see you in the next video.